Welcome, class. Recording for posterity and also for the people who are on field trips. Yesterday, which we did not capture on video because I forgot, we proved Lemma 8.4a, and I told you for homework to prove Lemma 8.4b. How successful were you?
Successful.
Good. Can you take out your packet? We're going to do it right now. I do have another packet in the down there-ish general region, in the shelf under the panda.
I got it.
Somewhere down there. Hopefully you'll see one. Okay, so what is Lemma 8.4b? It is the dual of Lemma 8.4a, and it says something probably like, let P be a point that is, I'll write this right now. Let P be a point that is on exactly n+1 lines. Distinct lines. Okay. Distinct lines. And goal, if show that if L is any line that does not contain P, then L contains exactly n+1 distinct points. If L is any line that does not contain P or does not go through P, then L contains exactly n+1 distinct points. Okay, let's begin. What do we have? We have a point P, and what do we know about this point P? We know that it is on exactly n+1 distinct lines. What would you like to call these lines?
L1 through Ln+1.
Woo! Yeah, excellent choice. So here's a line, here's a line, here's a line, dot, 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 dot. Here's a line. Let us choose to call these lines L1, L2, L3, up to Ln+1. Okay, so again, the picture is helpful for your brain, but the argument is happening on the paper with words. Here's what we know. We know that P is on L sub I for I between 1 and n+1. And I know that each of these lines is distinct. So Li is not Lj for I not equal to j. Cool? Cool. Good. Okay. So that was just us sort of writing out the condition of the theorem. Now, what does the theorem actually say? It says if L is any line that does not contain P, then L contains exactly n+1 distinct points. Okay, so take some line L and let it be over here, not going through P. So take line L, P not on L. And all we need to show to finish the proof is that L contains exactly n+1 distinct points. So show L contains exactly n+1 distinct points. Okay, good. Well, why does L contain exactly n+1 distinct points? The obvious answer is like why, just in words or hand gestures. Does L have n+1 distinct points on it? Yeah, man, there are all these n+1 lines, and what do all these n+1 lines do? They all meet L, and they all meet L somewhere different. That's like the one line, like, I don't really want to do math, I just want to I'm pretty confident that someone else can take care of the details like approach. Nah, man, we are the people that take care of the details. Let's go. You are right. Why do we know that each of these lines beats L at all? By one of our axioms. These should be getting increasingly familiar, these axioms. FPP2, which says that every two lines meet, or does it?
Every two distinct.
Every
lines.
two distinct lines. Good. So before I can invoke FPP2, I need to argue that, consistent with my picture, L is in fact distinct from each of these lines. Why is it?
Because it doesn't contain P.
Because it differs with respect to inclusion of P. Yeah. So so now is the time for like a preparatory note. P is on L sub I, but P is not on L by assumption. Conclusion, L is distinct from each of the L sub I. Okay, so since L is not equal to L sub I, by FPP2, we know that L intersects L sub I, yeah? That by FPP2, L intersects each L sub I at, what would you like to call that point?
PI.
P sub I, yeah. At P sub I. Good. So basically define the intersection of L and L sub I to be the point P sub I. Okay, cool. Now we can sort of draw the picture consisting with what we've just done. And the picture looks like this. And so this P1, P2, P3, etc., all up to Pn plus 1. Okay, good. Well, our goal was to show that there are n plus 1 points on this line L. So have we succeeded? Not quite, because what do we need to do? Two things, basically.
To show that the intersections are the same.
Yeah, we have to show that we really do have n plus 1 points. In other words, that none of these points are the same, right? We have defined these n plus 1 points, but we have to show that they're all distinct. Well, why are they distinct?
They can't be on the same line because you can do it with contradiction.
Wait, have I done something wrong yet? No. Sorry, zone out for a second. Yeah, why are they all distinct?
Because if two lines contain the same 2 points, then that's just a contradiction with BP1, I think. Maybe it's 2.
Well, then
It is, depending on how you write it, it's either one, yeah. Yeah, so there can't be, if two of these points were the same, then what is the problem with that, if two of these points were the same?
Then they share two. Then the two lines share two intersecting.
Yeah, say if P1 and P2 were somehow the same point, let's just talk it out. If P1 and P2 were the same point, then what we would have are all of the, then we would have like line, let's see, then line L1 and L2 would both go through P2. What's wrong with that?
They would have to be the same line for that to be possible.
They would have to be the same line, and they're not. Yeah, well, I feel like I've forgotten some small step, but maybe I haven't yet. Okay, so let's woo! Yeah, that's a video. You can download some videos too.
Okay.
Good, but can you put the phone on silent maybe?
Sorry, I just
Yeah.
I didn't know
Good.
how to start
So suppose that two of the don't worry, people watching at home. Someone is in the background downloading baby videos. So suppose that Pi was equal to Pj for some I not equal to j. Why is that impossible? Well, if Pi is Pj, then I have Pi on Li, and I have Pj on Li as well. Wait, is this what I want to do? No. Wait a second. What's going on? Pi is on Li, and Pi just is Pj, so that means, yeah, I guess I want to say that Pi is on Lj. Because after all, I've defined Pj to be the intersection of L and Lj. So if Pi just is Pj, then and Pj is on the intersection of L and Lj, then Pi is also on Lj. I think this is the best way to say it. What is wrong with this?
Like both also intersect P.
These lines both also intersect P, right? But I also have P on Li, and I have P on Lj. And have I shown that all of these, yeah, here was the thing I forgot to do, but which we might as well, it doesn't really matter, we can still do it now. What's the thing you would like to conclude right at this point?
That Li is not.
Well, in this case, Li is
Are you guys following this? Or lost, or the opposite of lost? All right, I'm getting some nods, which could mean anything because I asked opposite questions. Good. Notice that what we have here is, here's the general picture is, right? The general picture is, here's this line L, here's this point P, and what we're imagining sort of temporarily is that there's this point Pi, which is also Pj. What's wrong with that is that there are these two different lines, Li and Lj, which both met line L at now the same point. And what we would like to conclude is that this is a contradiction. What is the contradiction?
Two lines.
Can't intersect at two distinct points. But a small logical, we've made a small logical omission in our argument. Have I shown, in fact,
that P is not.
distinct from the Pi? No, I didn't. That's what I think I intended to do above, but I just didn't think of it. Anyway, we'll do it now. Why is P, in fact, distinct from all the P sub I?
It's not. P is not on that.
Yeah, good, but it still needs to be mentioned. So that is right. P is not on L, but each of the P sub I is on L by construction. So just like note that means that P is distinct from each of the P sub I, as our picture and common sense suggests, but we've now proven it rigorously. Okay, so since that is the case, then here I claim we have a contradiction. This is a contradiction with, depending on how you think of it, I think of it as a contradiction with FPP2, because FPP2 says that two lines intersect at a single point, but here we have two distinct lines intersecting at two distinct points. Okay, can I just leave that like as is? The distinct lines being Li and Lj, which are distinct by assumption, intersecting at the distinct points P and P sub I, because we showed. So this is a contradiction, and since this is a contradiction, that means that this supposition which we made here is false. So, in fact, Pi does not equal Pj. And now we have showed that these n+1 points on L are distinct. Okay, the last thing to do is to show, since we have to show that there are exactly n+1 points, we have to show that there aren't any others, yeah? Whew. Why could there not be any other points on L? Well, are you like keeping the camera moving and stuff? Good. So suppose there was some other point on L, say Q. Why? What's up with that point Q? Oh, he also used Q. Woo! What's up with that point Q? Why? What? Tell me. So I'll just write this here. Suppose that there is some point Q on L. There has to be a line PQ, she says. Can we insert a small bookkeeping step?
Q is not P.
Q is not P because P is not on L and Q is on L. Conclusion, P is not Q. So since P is not Q, by FPP2, 2, right? Yeah, no, 1. By FPP1, there is a line through P and Q. Let's call it, say, M.
It's not like-
Or let's not call it M. Let's just say there is a line. There is a line through P and Q. But, what do I know?
Wait, you have to do something else though. You have
Do
to
I?
show Q is not one of the ERs. Just
I'm going
by
to
definition, so-
I'm going to slightly do it differently than that. You'll see in a second. You could do that.
Okay.
But instead, maybe it's more elegant, but maybe it's more confusing. I can't decide. I'll just kind of leave it open as to what the deal with Q is. Q is just a point. But here's what I know. There certainly is a line through P and Q. But if there's a line through P and Q, tell me about the lines through P. There are only n plus one of them, but there are, by the assumption of the theorem, exactly n plus 1 lines through P. And those lines are, in fact, L1, L2, all the way up to Ln plus 1. So, like line PQ or whatever must be one of them, right? Are you guys with me? I'll just pretend that was everyone said so. Yes, must be one of them. So, say line PQ is like, I don't know, is L sub j, for example, for some j. Well, now, what do I know? I know that P is on L sub j, and Q is on L sub j. And so what? Wait, is this what I want to do? Sure. Starting to agree with Evan that it's more clear to just do it by contradiction. But if P and Q are on L sub j and P, wait a second.
You can say Q is the only intersection with L.
Yeah, I'm stumbling just finishing it off, but you're exactly right. And Q is on L. So my conclusion is that just like Q just is P sub j. Because P sub j is the intersection by definition. Maybe I'll just write this. Because by definition, the intersection of L and L sub j is P sub j. That's how we defined P sub j in the first place, right? To be the point where L and L sub j meet. But if there's this point Q that's on L sub j and also on L, then that means that maybe this is like the key point. That sort of little line is distracting. This is the key point, is that we have Q is, if we're deciding that Q is on this line L sub j, but Q is also on L, then L and L sub j meet at a single point, P sub j, so Q just is P sub j. Okay, so this is the way of doing it without making it a contradiction, but by just saying, look man, any point Q on line L has to be one of the previously named P sub P's because of this argument. Okay, how are we doing? Shrug. I got a shrug of shrug. Good enough. Good enough is pretty good. So we got these two lemmas. Let's emotionally grasp these two lemmas. We got the lemma 8.4a. I would like us to be able to apply this lemma so just smoothly and with warmth in our hearts. So what is lemma 8.4a? It says, what does it say? got a line. And it's got n plus 1 points on it. And there's a point P not on this line. P1, P2, P3, dot, 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 Pn plus 1. Then what do we conclude?
Plus one distinct lines.
That there are n plus 1 distinct lines through P. Okay, good. Now we have lemma equals B, which is the dual, which says, well, we just proved it, but it says that we have some point P, and there are exactly n plus 1 lines through P. Now, if you give me a line L, which P is off of, then conclusion, those n plus 1 lines on P meet at n plus 1 distinct points, P1, P2, P3, P. Alright, so lemma 8.4a says give me a point off a line with n plus 1 points, and there are n plus 1 lines through P. And lemma 8.4b says give me a point with n plus 1 lines through it off the line L, and those n plus 1 lines will meet L at n plus 1 distinct points, and there are no other points. Alright, how are we doing? Good, I'm going to stop the camera for a second. Just